Hello dear students, today in this lecture we will discuss the relationship between Lebesgue integral and improper integral. So this lecture deals with the relationship between improper Riemann integral, improper Riemann integral, improper Riemann integral and Lebesgue integral. Lebesgue integral. In fact, I would evaluate certain classical improper integrals with the help of certain classical improper Riemann integrals with the help of Lebesgue integration. In the first lecture on this, we have discussed the improper integral. We have seen that suppose we have a function which is Riemann integrable on every closed subinterval of this interval on bound interval a to infinity. So f is a function which is defined on this interval, and this f is Riemann integrable over every closed and bounded subinterval of a infinity. And if this limit exists, limit r approach to infinity, integral a to r fx dx. If this limit exists, then we will say that the improper Riemann integral exists, and we will denote it by a to infinity fx dx. Then we have seen that then we have proved the following theorem: if integral a to infinity mod of fx dx exists, then this integral also exists. A to infinity fx dx also exists. This we have seen. If the function mod of f, the improper integral of mod of f exists, then the improper integral of f also exists. But the converse is not true, and we have seen that an example of a function where we have seen this function f of x is equal to sin x divided by x. This function which is defined on the interval 0 to infinity. This function is defined on this interval 0 to infinity, and we have seen that in that lecture we have seen that the integral 0 to infinity mod of sin x divided by x dx, this limit is equal to this integral does not exist. We have seen this does not exist. Then we will see that in our coming lecture we will see that the integral 0 to infinity sin x by x dx, this integral always exists. Okay, but the integral this one it does not exist. So it means that the existence of the f improper integral of f over the interval 0 to infinity does not imply the existence of the integral mod of f, but its converse is always true, which we have seen in our theorem. So today in this lecture we will discuss the relationship between the existence of improper integral and the existence of the Lebesgue integral. That theorem is very important for our discussion. So let us first state that theorem. The statement of the theorem is: let f be a function from the interval 0 to infinity, from the interval a to infinity to r, and this function is Riemann integrable. It is given be Riemann integrable. It's Riemann integrable. It's Riemann integrable over every closed bounded subinterval of over every closed and bounded subinterval of this interval a to infinity. Okay, And then following holds. Then f is Lebesgue integrable. Then f is Lebesgue integrable if and only if the improper Riemann integral, if and only if the improper Riemann integral, if and only if the improper Riemann integral a to infinity mod of fx dx exists. Moreover, in that case, moreover we have this. In this case, we have the following. Moreover, in this case, the Lebesgue integral and the improper integral both are equal. The Lebesgue integral of f over this range is same as the improper integral. 0 to infinity mod of fx dx. It's not mod here, it's without mod. Okay, it's without mod. But this is always only true if the improper integral a to infinity mod of x exists. So existence of this interval, the integral a to infinity fx dx, does not imply that f is Lebesgue integral, and we don't have, in that case we don't have this equation. Okay, so this तो ये इस पॉइंट को आप क्लियर कीजिए. तो यहाँ से इक्वेशन से आपको ये पता चलता है कि अगर ये इंटीग्रल एग्जिस्ट होगा, सो देन इट इम्प्लाइज दैट दिस एफ डी लैम्डा इज इक्वल टू इंटीग्रल दिस, बट दैट्स नॉट ट्रू. सो it's important that the integral a to infinity mod of x dx should exist. Then this equation holds. Then f is integrable. Then improper integral of f also exists, and improper integral of f is equal to the Lebesgue integral only if this integral exists. The improper integral of mod of fx dx exists. Okay, let's prove this theorem. So this is a statement of this theorem. So it's given that f is Riemann integrable over every closed and bounded subinterval of a to infinity. Then these two statements are equivalent. F is Lebesgue integrable if and only if the improper Riemann integral a to infinity mod of x dx exists. And in that case, we have this equality of the Lebesgue integral and the improper integral of f. Okay. So let's prove this theorem. Prove. Assume that f is Lebesgue integrable. Assume that our function f is Lebesgue integrable. Okay, over this interval, over the interval a to infinity. So this is. Then we know that f plus as well as f minus both are integrable, Lebesgue integrable. Then f plus is also Lebesgue integrable, is also Lebesgue integrable over this interval, over this a to infinity. So let's take the sequence Rn of numbers such that limit of Rn is equal to infinity. Let Rn be any sequence in the interval a to infinity such that limit of Rn and approach to infinity is equal to infinity. Okay, we can choose that sequence. So you can, in particular, you can choose a plus n. Just so you can solve the numbers in this interval such that the limit of that, so you can limit of a plus n is infinity. In particular, that's the particular series. Now for each n we define fn. For each n greater or equal to 1, we define fn. What's this fn? Let's take this fn of x is equal to, it's equal to f plus x. F plus x is Lebesgue integrable if x is in the interval a to Rn. Let's define this function, and it's 0 elsewhere, and fn of x is equal to 0 if x is greater than Rn. That means if x is not in this interval, if x is greater than Rn. If x is greater than Rn, then you can easily verify that. Then one can easily verify that, this limit of fn, limit n approach to infinity of fn of x, it's equal to f plus of x, because whenever n is approaching to infinity, this will be x belongs to a to infinity. So in that case, thus this limit must be equal to f plus x over the whole interval a to infinity. And one more thing is that 0 is always less or equal to fn x, and fn x is always less or equal to f plus x. Fn x is always less or equal to f plus x. This is always true because it's equal to f plus x if x is in this a to Rn, and elsewhere it's equal to 0. But this f plus is always non-negative quantity. It's always non-negative, so it means that fn x is always less or equal to f plus x in general. So in fact, this on this interval it's equal to f plus x, but outside of this interval fn is 0. But outside of this interval a to Rn, f plus x is greater or equal to 0. So I can say that this fn x is always less or equal to f plus x, and it's also greater or equal to 0 because it's either equal to f plus x or equal to 0. But f plus x is a non-negative function. So we have this 0 is less or equal to, also we have 0 less or equal to fn x less or equal to f plus x, because this fn x is either 0 or it's f plus x. This is true for all x in the interval a to infinity. Also, since f plus is integrable, 0 is integrable, it's a constant function, and f plus is a measurable function. Fn is a measurable function because this fn x is equal to f plus x if x is in the interval a to Rn and it's 0 elsewhere, so it's measurable function. Fn is a measurable function since this fn is measurable and lying between two integrable functions, two Lebesgue integrable functions. So therefore fn is Lebesgue integrable and it's dominated by f plus x. So it's a dominated. So we can apply the Lebesgue dominated convergence theorem here. So Fn is Lebesgue integrable such that we have following integral Fn d lambda, it's equal to integral a to Rn Fn of x and dx. This is true. It's f plus, sorry, it's here f plus. Okay, it's not Fn, it's f plus x dx. So actually it's equal to the integral over a to Rn plus integral over Rn to infinity, but a to Rn Fn is equal to f plus x, and Rn to infinity, this Fn is 0, so it's a to Rn f plus d lambda, which is equal to a to Rn f plus dx, because it's Riemann integrable over every closed subinterval. Okay, it's Riemann integral over this interval a to Rn, so its Lebesgue integral is equal to its the Riemann integral over the interval a to Rn, and outside of this interval its Fn is 0, and inside the interval value of Fn is equal to f plus x. So also this, and such that this, and we have also this property Fn of x is less or equal to f plus x, so we can apply the Lebesgue dominated convergence theorem. So by Lebesgue dominated convergence theorem, by Lebesgue because this sequence of integrable functions is dominated by some integral function. So by Lebesgue dominated convergence theorem, we have integral of limit n approach to infinity Fn d lambda is equal to limit n approach to infinity integral Fn d lambda. So which means that, but this limit is equal to f plus d lambda. This is equal to the limit and approach to infinity, and this is actually the Riemann integral. Here it's the Riemann integral. It's a to Rn f plus x dx, f plus x dx. So this shows that the improper Riemann integral, this implies, this shows that this exists because f plus is Lebesgue integrable. So therefore integral a to infinity f plus x dx exists. Okay, exists. Similarly, we can see that similarly we have integral a to infinity f minus dx exists, and this is equal to integral, in fact this is equal to f minus d lambda, which exists. So therefore f, which is equal to f plus minus f minus, and mod of f, which is equal to f plus plus f minus, are both therefore the improper Riemann integral of both the functions. So therefore this function since we have this f is equal to therefore the improper integral, therefore the improper, you can write this here, this, therefore the improper integral of f equal to f plus minus f minus, and mod of f is equal to f plus plus f minus also exist, this improper integral also exists. And not only this, integral a to infinity fx dx, which is equal to integral a to infinity f plus x dx minus integral a to infinity, because both exist actually, f minus dx okay, and this one f plus it's equal to the Lebesgue integral of f plus d lambda, and this one it is a Lebesgue integral of f minus d lambda, and this is equal to integral of f plus minus f minus of d lambda. So I will write this line here. So this is equal to integral of f d lambda. So thus the improper integral a to infinity fx dx is equal to the Lebesgue integral f d lambda. Now we prove its converse part. For the converse, assume that this integral a to infinity mod fx dx exists. So this implies the integral a to infinity this fx dx also exists. So both the integrals exist. So clearly we have the following limit integral a to a plus n mod of fx dx. This is equal to integral a to infinity mod of fx dx. Because this limit exists, therefore this is equal to a to infinity, which is equal to the finite thing, which is equal to finite. Now we defined name it 1 here. Let's define the following functions. So this should note this limit a to a plus n f mod of x is equal to a to infinity mod of fx, because the improper integral a to infinity mod of x exists. So that's why this limit is equal to this. Okay. So let's name this equation 1. Now we define the following functions. Define f n x, which is equal to mod of fx. It's a non-negative function. So f n is a sequence of non-negative function. This should be clear. X belongs to the interval a to a plus n, and it's equal to 0 elsewhere. So this sequence is either 0 or mod fx, but mod fx is not equal to, it's always greater or equal to 0 over whole the interval a to infinity. So it means that also you can see that this fn is increasing sequence, because you can see this fn plus 1 x is equal to mod of fx if x belongs to the interval a to a plus n plus 1, and it's 0 elsewhere. So but it's equal to mod fx only on this interval a to a plus n. This interval is bigger than this. So it means that fn x is less or equal to fn plus 1x for all x. This is true for all x. This is true for all x. So also we can see the limit. What's the limit of fn? Limit of fn x. it's equal to mod of x. You can see it's when this n is approaching to infinity. So this fn x will approach to mod of fx, because in that case it cannot be 0 on any part, because whenever n is approaching to infinity, this interval will become a to infinity and it will be equal to mod of fx. So limit of fn x is equal to mod of x. So therefore we have this 0 less or equal to fn x, and fn x increases to mod of fx because it is an increasing sequence, and the limit of fn is equal to mod of fx. It increases to mod of fx, and this is true. This is true for all x, for all x belongs to the interval a to infinity, or you can say for all x greater or equal to a. This is one and the same thing. Now it's given that this what's fn? It's mod of x if our x belongs to a plus n and it is 0 elsewhere. So it means that but mod of f is Riemann integrable. Mod of f is Riemann integrable over any subinterval or any closed subinterval. So therefore this fn, it's Riemann integrable. It's Riemann integrable over a to a plus n. Why? Because fn is equal to mod f on this interval. And mod f is Riemann integral over this interval. So fn it's Riemann integrable over this interval for each n greater or equal to 1. And it's this means it's Lebesgue integrable, because every Riemann integral function is Lebesgue integrable on over this interval. So fn is Riemann integrable. So fn is an upper function. So this means that fn is an upper function. Is an upper function over the interval a to infinity. It's an upper function because fn is Riemann integrable over this interval and it's 0 elsewhere. So that means this fn is an upper function over the interval a to infinity, because on the outside of this interval a to a plus n, fn is equal to 0. So that means on this interval, if we restrict our function on this interval a to a plus n, the function fn is an upper function because it is non-negative and Riemann integrable and is Lebesgue integrable. And any integrable function which is also non-negative is always an upper function. That you have already done. So fn is an upper function on this interval a to a plus n, but on the rest of the part of this interval a to infinity, on the rest of the interval, its value is 0. So that means fn is an upper function over whole the interval a to infinity. It's an upper function over whole interval a to infinity, and it's satisfying the following property. Satisfying this property, satisfying this integral fn d lambda, this integral because it's the integral over a to a plus n, because on the rest of the part its value is 0, but on that interval it's Lebesgue, it's Riemann integrable, so its value is a to a plus n fn dx, because both Riemann and Lebesgue integrals are same whenever the function is Riemann integrable. But on this range a to a plus n, this fn is Riemann integrable and its value is equal to this value of fn is equal to, they are same, but on the remaining part of this interval, outside of this interval, its value is 0. So this is equal to this Riemann integral a to a plus n fn dx. This is very simple, because क्योंकि आप इस इंटरवल से बाहर जब आप जाओगे a to a plus n, fn का वैल्यू 0 है. So fn d lambda is equal to the integral over it is equal to the Lebesgue integral over this interval a to a plus n plus the Lebesgue integral over the complement of this set. But over that set, over the complement of this set, the value is 0, therefore the Lebesgue integral is 0. But over this interval a to a plus n, the Lebesgue integral is equal to its Riemann integral. And this is equal to, but at the same time this Fn is equal to the mod of f. It's mod of fx dx. It's mod of fx dx. And this limit exists actually, so we can say this limit is finite, so we can say this limit n approaches to infinity. So this implies that limit n approaches to infinity integral f and d lambda, it's equal to integral a to infinity mod of fx dx, which is a finite thing, and fn is a sequence of upper functions. So which means that for mod f we have a sequence of upper functions such that this limit n approaches to infinity integral of mod of integral of this fn is finite, which means that this f is also an upper function. Because we have a generative sequence for this, it's also non-negative, so it's actually integrable, but at the same time it's also non-negative, which means that it is an upper function actually. So this function is an upper function, which implies mod f is an upper function and hence Lebesgue integrable, and hence Lebesgue integral. It's Lebesgue integral. Mod f is Lebesgue integrable. But f is measurable. F is measurable because f is Riemann integrable. Riemann integrable. F is Riemann integral over any closed and bounded subinterval, closed and bounded subinterval of a to infinity. So that means we can define the sequence on that. We can define the sequence. We can define this like sequence fn. So actually this f is the limit of fn. So in that case, if you do like this here, if you define fn is equal to f on a to a plus n and it's equal to 0 elsewhere, then this fn it's a sequence of Lebesgue integral functions, because this f is the Riemann integral over this interval and it is 0 elsewhere, therefore it's Lebesgue integrable, therefore it's Lebesgue measurable, not yes, it's Lebesgue measurable. This function f is Lebesgue measurable over a to infinity because it is it's Riemann integral over the finite interval a to a plus n and its value is 0. So this fn it's a sequence of is a sequence of measurable function, you can see, and limit of fn is equal to f, so therefore f is also measurable. So thus our function f is measurable and mod of f is Lebesgue integrable, and f is measurable. This means this f is measurable here, it's measurable, so this means f is Lebesgue integrable, f is Lebesgue integral. The function f is Lebesgue integral. So that means whenever the improper integral a to infinity mod of fx dx exists, then f is Lebesgue integrable. Now we have to prove the equality of the integral. The improper integral and the Lebesgue integral, they are actually equal. And this equality follows from the previous case. Actually, whenever f is Lebesgue integrable, then we have done that the improper integral exists and the value of the integral, they are both equal. So thus we have proved this theorem completely. इक्वलिटी ऑफ इंटीग्रल तो पिछले पार्ट से ही फॉलो हो रहा है ना, क्योंकि अब आपके पास f आ गया Lebesgue इंटीग्रेबल, और जो पहला पार्ट आपने इसका किया वहाँ पर आपने क्या किया, आपने ये माना कि अगर f Lebesgue इंटीग्रेबल है then the improper integral exists and the integrals are equal. The improper integral and the Lebesgue integral both are equal. So this proves the theorem completely. So next we discuss two important theorems which we use to evaluate the improper integrals, and that we call actually the differentiation under integral sign. So for this we first prove the following theorem. इस theorem का जो statement है it's much bigger than the proof of the theorem, you can see. So let's take a major space. Let X as mu be a major space. Be a major space. Okay, and J be a subinterval. And J be a so interval means it's a subset of real line. Subinterval of R. So this is any major space X is mu, and let's define a function f from X cross J to R be a function such that if we fix any t, then this f, which is a function from X to R, by fixing t, this is a measurable, is measurable for every t in the interval j. If we fix any t in the interval j, then this will be the measurable function. So for instance, I will explain it here like this. Suppose our X is whole R, okay, and we define a function from X cross J to R by f of X comma t equal to, say, it's equal to x square plus t. So let's fix some t. So if this function is it means that this function is measurable for each t, for each fixed t belongs to G. So say if I take a j equal to the interval closed interval 0 1, so if I take this say t equal to 1 by 2, fx 1 by 2, this should be measurable. It's equal to x square plus 1 over 2. So this should be measurable. So measurable for t means that if we fix any t, then it will be the function of x only in that case, and that function of x should be measurable. Then in that case it will be a function from x to r, just a function from x to r by fixing t. Okay, for each t in J, this function should be measurable. This function should be measurable. Assume also that there is an integrable function. Assume also that there exists an integrable function. There exists an integrable function. There exists an integrable function g such that it's dominated by g, such that mod of f of xt is less or equal to gx for all t in G. So it's like the sequence of function. In case of dominated convergence theorem, we have a sequence of function. Instead of t belongs to interval 0 in any interval 0 1, and we are taking these are the natural numbers. F and x in that case is less or equal to gx for each n greater or equal to 1. So here we have we are taking this set j actually instead of n. So it's the situation is like that. So fxt is less or equal to gx for all t belongs to G. That means this class of measurable function, it's a measurable function for each t. This class of measurable function, this collection of measurable functions is dominated by some function gx uniformly. It's true for each t belongs to G. This gx is independent of t. and this is almost for almost all x's, for almost all x, for almost all x. Now if for some accumulation find, so we are given that x as mu is a major space, and this is a function which is measurable for each t, such that there is a function g, such that with this condition that this is dominated by, this collection is dominated by g of x for almost all x's, where g of x is an integrable function. Now if for some accumulation point, if for some accumulation point, if for some accumulation point t naught of j, there exists this accumulation point may be infinity, okay, it may be plus infinity or minus infinity. There exists a function h, there exists a function h, there exists a function h such that limit t approach to t naught f of xt is equal to h, this limit exists in R, okay, this should exist in R, so it's a function of h which exists in R, h of x here, okay, for almost all x, for almost all x, for almost all x, for almost all x, then h defines an integral function, then h defines an integrable function. It's actually it's like it's Lebesgue dominated convergence theorem, actually it's like that, because in that case we are taking an approach to infinity fn x, that's equal to fx, then we are showing in that, then we are showing that that fx, that limit function, is Lebesgue integrable. So here again we have a limit function, actually hx, an integrable function because it contains this t naught may be infinity, but and in that case the infinity is actually, you are taking the limit at infinity in that case. So an integrable function, h defined as an integrable function, and the limit of the integral is equal to the integral of the limit. That's important for the, so this is actually some sort of generalization of the Lebesgue dominated convergence theorem. You can see f of xt integral here, this should be equal to the integral of the limit of this, that is equal to h, okay, that's equal to h. So this is our theorem. So again I will show this the statement of the theorem. So this is the statement. We have a major space, we have a bounded we have a subinterval of R, this interval may contain this the infinity may be the accumulation point of this interval, so this interval may be unbounded interval, okay, j may be an unbounded interval, and we have a function f from x cross j to R which is measurable for each t in j, and also we have a function g such that this is dominated by g. Then for any accumulation point t naught of t, we have this limit t approach to t naught f x t hx, this hx is defined as an integrable function, and this holds. So let's prove this theorem, proof of the theorem. So assume that the function f from x cross j to R satisfies the hypothesis of the theorem. Satisfies the hypothesis of the theorem, satisfies the hypothesis of the theorem. And let's choose, because T naught is an accumulation point of T, so we can find the sequence Tn in J. Let Tn be a sequence in J, such that limit n approach to infinity, Tn is equal to T naught. Now let's define Hn. Define Hnx, which is equal to f of x Tn. So you can see the similar steps as in the Lebesgue dominated convergence theorem. Now we have here constructed the sequence of functions which is Lebesgue integrable, which is measurable, and that sequence is dominated by integrable function. Okay. Then this is true for all x and x. For all x and x, let's define this sequence. Then we have this mod of Hn is less or equal to G, because mod of Hn is equal to mod of fxtn, but mod of fxtn is less or equal to G. So let me write the complete steps here. So we have mod of Hn of x, which is equal to mod of f of x Tn, but in the given hypothesis this is less or equal to Gx. So it means that this Hnx, it's a measurable function and it's less or equal to Gx, but at the same time it's also greater or equal to Gx. So that means Hnx lies between two integrable functions and Hn is measurable. So therefore Hn is a sequence of measurable functions such that minus G less or equal to H less or equal to G, and G is integrable, therefore Hn is a sequence of integrable functions. So this is very important. It is a sequence of integrable functions actually. So, and this sequence is dominated by G. So by Lebesgue dominated convergence theorem, we have the following. We have this limit of integral of Hn is equal to integral of limit of Hn. This means limit of integral of Hn means, but Hn is actually fx. Hn is here. So what's Hn? Hn is here fxtn. Fxtn, it's equal to integral of the limit of fxtn and approach to infinity. So this means that but limit n approach to infinity Tn is equal to T naught actually. This means that limit T approach to T naught, it's one and the same thing, integral fxt, it's equal to integral, but the limit n approach to infinity Tn, it is same as the limit T approach to T naught f of xt, and that's equal to integral, or this this limit of Hn is actually h also, it's actually h. Because limit n approach to infinity fxtn is same as limit t approach to T naught fxt. So both are actually c. So limit t approach to T naught fxt is equal to integral limit t approach to T naught fxt. Now in the next theorem we check the differentiation under integral sign actually, and for this we first make some notations. We use the notation, some notation in that theorem, so let's discuss those notations first. If f is a function from x cross interval a to b, open interval, to r, is a function if this is a function and t naught belongs to ab, t naught belongs to ab, then its difference quotient at t naught, we define the difference quotient function, then its difference quotient function at t naught is defined by this. That's the notation of this t naught of xt. It's equal to fxt minus fxt naught divided by t minus t naught for all x in x, and t belongs to ab. So in order to define it at every t, so we take dt naught at x comma xt at t equal to t naught, we take its value equal to 0. We take this also, we define this dt naught at x comma t naught, its value at t naught, we take this value equal to 0, because for t equal to t naught the denominator is infinity here, so we define its value separately. At t equal to t naught, we define dt naught xt naught is equal to 0 for all x in x, So this function is called a difference quotient function at t naught, dt naught xt, which you have defined here. So whenever this limit t approach to t naught exists, then this is just the partial derivative of fxt with respect to t at t naught. So if limit t approach to t naught dt naught x comma t exists, then what's this limit in that case? Limit t approach to t naught dt naught x comma t, it's equal to limit t approach to t naught fxt minus fxt naught divided by t minus t naught. This is just the partial derivative of f with respect to t at t equal to t naught. So whenever this limit exists, it's equal to the partial derivative. So next theorem is very important. So what's the next theorem? Let's state that theorem. Let xs mu be a major space. Let xs mu be a major space, and let f be a function from x cross ab to r, be a function such that this f t is Lebesgue integrable, for all t belongs to ab. Assume that for some t naught, for some t naught belongs to AB, for some t naught belongs to AB, the partial derivative df dt at the point t naught, this exists, this partial derivative exists for almost all x, for almost all x. Suppose also that there exists an integrable function. Suppose also that there exists an integrable function g, and a neighborhood v of t naught, and a neighborhood v of t naught, such that this is dominated by g, this partial derivative in the neighborhood, okay, is less or equal to gx for all x in x, for almost all, okay, for almost all x, and this t belongs to v, then the conclusions. First property, this is an integrable function, this partial derivative, who can integrate this at t naught, okay, defined as an integrable function. And the second property, which is very important, which we will use, the function f from closed interval AB to R, defined by f of t is equal to the integral fxt d mu, which is integration with respect to measure, is differentiable, this function is differentiable at t naught, it's differentiable at t naught, and f dash t naught is equal to the derivative, it's the derivative of this function with respect to t at t naught, that's equal to integral of the partial derivative at t naught. So this is very important here. This f of t is equal to integral fxt. This defines this is a differentiable at t naught, and its derivative is equal to integral of the partial differentiation. So derivative of the integral is equal to integral of the partial derivative actually. Okay. So this is the statement of this theorem. It's a measure space, and we have this partial derivative. This is there is a partial derivative, exists partial derivative for almost all x, and suppose also that this partial derivative has the following properties, that this limit t approaches to t naught, the partial derivative exists, then the limit of t approaches to t naught, okay, this is this partial derivative exists, and there is a function g such that this divided difference function, quotient function, is dominated by the function g, which is Lebesgue integrable. Then you have to show that the partial derivative at t naught is integrable, and its integral is equal to this, and its integral is equal to f dash t naught, where f of t is this. So let's prove this theorem. We have to apply the previous theorem here actually. So let's make this following assumption. Put dI by dt partial derivative because it's almost everywhere actually. This partial derivative equal to 0 for at each point x, at we take its value equal to 0 at each point x where this partial derivative does not exist. Where? Because partial derivative exists almost everywhere. Partial derivative does not exist. Okay, does not exist. Then this limit, then the limit t approach to t naught dt naught of this function xt, which is equal to the partial derivative at the point t naught, holds for almost all x, for almost all x this partial derivative exists. For almost all x. By previous theorem, this limit defines an integral function. By previous theorem, this df by dt naught at df by dt at t naught, df by dt at t naught, okay, df by dt, this partial derivative at t naught defines an integral function, because this t naught is an accumulation point actually, defines an integrable function. Integrable function because that the divided difference quotient is dominated by function g, so therefore the limit of that divided difference quotient will define an integrable function. Define the integral function, and what's that? This f of t. Let's calculate this f of t minus t naught divided by t minus t naught. F of t is given; it's a function which is equal to integral divided difference. What's this f of t? F of t is equal to integral fxt. So this is equal to integral f of xt minus fxt naught, because ft naught is integral fxt naught divided by t minus t naught, and this is equal to integral, but this is the divided difference, this is dt naught of xt, okay, the integration with respect to mu d mu. And if t is approaching to t naught, this integral will approach to, this integral is approaching to, because we can pause the limit actually, so let's apply the limit on both sides. So this implies limit t by previous theorem, limit t approach to t naught f of t minus f of t naught divided by t minus t naught, it's equal to the integral limit t approach to t naught. We can pause the limit through integration by previous theorem, dt naught of x comma t d mu, but that limit is a partial derivative actually, and on this side it's actually f dash t naught. So f dash t naught is equal to this. This proves the theorem completely. So in our coming results, so we make the following from this theorem, we will make the use of following statements actually. So what's the first one is that So because here we have assumed that this partial derivative, this the partial derivative, it's we have assumed that in our assumption, in our theorem, that this the divided difference dt naught x comma t, it's less or equal to some gx. Okay, it's less or equal for all t belongs to t. So this neighborhood actually depends upon t naught, because v is a neighborhood of t naught. Okay, so first thing that we are going to do in our coming lectures, in order to calculate the improper integrals, that the partial derivatives, the partial derivatives df by dt of xt, of xt, these partial derivatives exists for all x, and all t belongs to v, where v is the neighborhood of t naught. This is a partial derivative at t naught. Actually, these partial derivatives should exist. Second thing that we have seen, there exists a non-negative integral function. There should exist non-negative integrable function g. There should exist this function g, such that mod of the partial derivative, this mod should be less or equal to g of x for almost all x, and t belongs to the neighborhood v, where v is the neighborhood of t naught. Okay, it depends upon the point t naught. So if we prove for certain function these two assumptions will hold, then we can apply this theorem, and we'll see that we can apply some classical improper